Solutions do tend to not follow Rolle's law, especially when you're dealing with solutes. The solutes typically don't follow Rolle's law. They follow what's called Henry's law. The concentration, Henry's law basically says that the concentration of a volatile solute in a liquid mixture is directly proportional to its partial pressure in the vapor. Okay? So now the proportionality constant depends on what units you're using for your pressure and your concentration. What we're saying here is this. Here's a mixture. Okay, so let's say it is liquid A plus volatile solute B, and then you have B in the vapor and A in the vapor as well. Okay, the partial pressure of let me change this up. Let me fix that up for consistency with what I have written here. Let's just say you have water, okay, just to make things simple. Let's say you have water here and you have some A in water, okay, and A happens to be a volatile solute. So you're going to have water vapor here in equilibrium and gaseous A, okay, so you have A gas in equilibrium with A in aqueous solution, okay. The partial pressure of A in the gas phase is directly proportional to its concentration in the liquid phase. So it's directly proportional to its mole fraction, if we want to use mole fraction as our way of expressing concentration. Okay, so in other words, you can say then that P sub A over XA is equal to a constant. Okay, or you can say X sub A over P sub A is equal to a constant. Anytime two things are directly proportional, the ratio of those two things is a constant. Okay, so whatever the constant is, it depends on how you write your equation. And so we generally refer to that constant as K sub H. Okay, this is K sub H. All right, and the unit for K sub H depends on how you express your proportionality. What do you put in your numerator? What do you put in your denominator? And so when you look these constants up from handbooks, make sure you check the units, because the units will tell you how the proportionality relationship is expressed. Okay, so if your K sub H, your constant is in pressure, that means this is the relationship. You have pressure over mole fraction. Mole fraction is unitless. What would be the unit for K sub H if this is how the concentration and pressure are expressed? Let's say concentration of A over partial pressure of A is equal to Henry's law constant, K sub H. What would be the unit for K sub H here? What's the unit for A? Concentration of A? Moles per liter, right? And what's the unit for pressure? Atmosphere or torr or whatever. So your case, if you see a Henry's law constant given as moles per liter per atmosphere or moles per liter per torr, okay, that means this is the expression that is used, that constant is being used for. Okay. What if your unit is, what would be your unit if your expression is pressure over molality? If your Henry's law constant is given as the ratio of pressure to molality, what's the unit for pressure? Torr or atmosphere, right? What would be unit for molality? Moles per kilogram, right? So that's one possible unit. So your Henry's law constant would be given in atmosphere per mole times kilogram. Okay? So just be aware of that when you're doing Henry's law problems. Keep track of the units because it tells you what the equation is that's being used. Okay? So anyway, what this is saying is the higher the partial pressure, so the more concentrated the solute is in the gas phase, that means the higher its concentration. So you have more, the higher the partial pressure in the gas phase, the higher the concentration in the solution. That means the more soluble it is in your solution. Okay. So let's look at an example. If you open a bottle of soda, carbon dioxide comes out of solution. The bubbles you see, that's CO2, carbon dioxide coming out. That's why it's called carbonated, right? This suggests that the pressure of CO2 in the sealed bottle is higher or lower than the partial pressure of CO2 in the atmosphere. In the sealed bottle versus when it's open to the atmosphere. Higher or lower? So the answer is higher. Good. Okay. Pressure is directly proportional to the concentration. The fact that the carbon dioxide bubbled out means what? When you open it up, you've lowered the solubility. So that's why it comes out. Otherwise, it will not bubble out if the solubility has increased, right? Okay. Estimate the molar concentration of oxygen in water if it is saturated with oxygen. So if your water can hold the most oxygen that it can hold, what would be its concentration? Your Henry's law constant for oxygen in water is 1.3 times 10 to the negative 3 moles per liter per atmosphere, and air is about 21% oxygen. Okay, so the air you breathe is mole fraction of O2 in the air is, let's call that YO2, is equal to 0.21. So what's the partial pressure of O2 in the atmosphere? If air is 21% oxygen, what's the partial pressure of oxygen in the air? What's the pressure of the air typically? 1 atmosphere. So what's 21% of 1 atmosphere? 0.21 atmosphere, right? So you say mole fraction of O2 is PO2 over P total. Okay? And you're given that the mole fraction is 21%, or mole percent is 21%, so your mole fraction is 0.21, and your P total is 1 atmosphere. So partial pressure of oxygen in the atmosphere is mole fraction of O2 times the atmospheric pressure. So it's going to be 0.21 times 1 atmosphere. So it's going to be 0.21 atmosphere. Okay? Now let's look at our Henry's law constant here. Look at the unit for Henry's law constant. Molarity over atmosphere. So what's our equation for Henry's law? What goes in the numerator? Something that has molarity, right? So concentration of O2 goes in the numerator. What goes in the denominator? Pressure quantity. So partial pressure of O2 must be in your denominator. So that's equal to 1.3 times 10 to the negative 3 molarity per atmosphere. That's your case of H. So can I solve for concentration of O2 now? Concentration of O2 is equal to K sub H times, this is K sub H, right? Times the pressure of O2, partial pressure of O2. So that's 1.3 times 10 to the negative third moles per liter per atmosphere times the partial pressure of O2 is 0.21 atmosphere. Okay? So what is that number? One point three times 0.21 is 0.273 times 10 to the negative 3 equals 2.7 times 10 to the negative 4. Okay. Moles per liter. Notice that's a very small number. Okay? So in cases like this, typically when you look for solubilities of oxygen in water, you probably encounter this in your biology classes. You've heard of dissolved oxygen. Okay, they're given in ppms. So let's convert this to ppm. Anytime you've got very low concentrations, it's better to express them as ppm. So this is going to be 2.7 times 10 to the negative 4 moles of O2 per liter of solution, right? So how do I convert moles to grams? What's the molar mass of O2? 32 grams, 32.00 grams per mole. So moles cancel out. And that would give me, and then ppm is what? It's milligram per kilogram, right? Or milligram per liter if it's very low. So let's change this to milligrams. So 1,000 milligrams per gram. So that gives me how much? 2.7 times 10 to the negative 4 times 32 times 1,000. That's 8.7 ppm. Okay, 8.7. So that is 8.7 milligrams per liter. Okay? Milligram per liter is ppm, provided the number that goes with it is a small number. When you're dealing with very dilute solutions, a liter of aqueous solution is essentially equivalent to a kilogram of solution, because water has a density of 1 kilogram per liter. Okay? Now, so this is equal to ppm only when you're dealing with very dilute solutions. And that's usually the cases where you use ppm anyway, when you're dealing with very dilute solutions. And for as long as you're dealing with aqueous solutions, then milligrams per liter is essentially the same thing as milligrams per kilogram, or ppm. So 8.7 ppm is as much oxygen you can put in your water to dissolve it in the water.